that you're creating. So it may well be the voltage is firing the neurons, sort of like an action potential. Or maybe it's heating. You know, you can, there's something called diathermy, where you put your hand in and the magnetic field causes electric fields, gets ions to move in the air, so you can warm things. In fact, there are stoves. I think there's a stove like that where it's an electric stove, and inside is just a varying magnetic field, and if you put a metal skillet on there, it's going to make eddy currents in the skillet, and it will warm the pot. So instead of heating with fire, you can use eddy currents to do that. Do you have that at home by any chance, anybody? It looks pretty fancy because you just have this flat thing, and it doesn't radiate any heat on its own, but it just heats the metal because it's driving currents, and the currents are going through a metal with resistance. It's going to get hot. So that's an induction heater, which they use. I think they use that even for melting aluminum or something like that. It's pretty crazy. Okay, now the thing I wanted to get to, this is actually a fairly important idea that we'll use later. And that is the idea that we talked so far about there being an EMF coming out of the wire. It's sort of like a battery because it can drive current through various objects, circuits. But if you push the idea a little further even, you could say that if I have a dB/dt, or d/dt here, and I have an EMF, there was a time when we said that EMF, or voltages, or EMF, voltage, we spoke about voltages, was the integral of the electric field times the distance. That's something you better know for exam 1. In other words, the electric field is sort of the gradient of a potential. The faster the potential changes, the stronger is the field, is another way of looking at that. So the idea is, could we use this idea, talking about this potential or this EMF that's being generated by the dB/dt. In other words, is there a electric field somehow in the space? Now this is a little funny idea because this EMF is around the loop because there's a potential difference between here, which would suggest that there's kind of an electric field along the loop, going around the loop, something like this, such that if you integrate the electric field around the loop, which is what that says, suppose I integrate this around the loop, then I will get the EMF that I observe. So this is an interesting idea because what it's saying is that when you change the magnetic field, you're actually creating a kind of circular electric field in the space. That's a different idea from this even, because this said I can get an electric field out of the Lorentz force because, in this case, I had a piece of wire there, and I was moving the wire, and the wire has electrons in it, and the electrons move from one side to the other, and so it builds up a field, but you have electrons there to make the field. This is an even different idea, not obvious really when you think about it, that even without the wire there, you're going to create an electric field in the space. That's a pretty amazing idea, but it turns out that it's right, apparently, because later on we're going to need this to understand electromagnetic waves, because what we're going to get is that we're going to make a wave where we're going to have a varying magnetic field in empty space, like between here and the sun. You're going to have a varying magnetic field, which will produce, dB/dt will produce, or dφ/dt will produce an electric field, and we'll see that this changing the electric field can produce a magnetic field. So the wave kind of supports itself. The magnetic field changes, produces an electric field. The electric field changes, produces a magnetic field. And the whole thing travels along at the speed of light. So by these time-varying fields, it turns out we'll be able to understand electromagnetic radiation, electromagnetic waves, including light, radio, microwaves, the whole spectrum. Radio waves, TV waves, cell phone waves, all electromagnetic waves. And it comes out because we're able to say that the changing magnetic field actually produces, in empty space, in the absence of any material, an electric field going around the magnetic field. It's pretty amazing, but you would say, I don't believe it, except that it works. So we have to keep that in mind. That is, we're actually inducing electric fields in empty space by a changing magnetic field. It's big stuff. This is very big stuff, I would say. Okay, now we can step back from that glorious, brilliant idea, back to a little more mundane thing, the solenoid, which we sort of passed over quickly before, because we talked about Ampere's law, and we gave an example of how you apply Ampere's law. We have to go back to this because we're going to generate the idea here of the energy in an electromagnetic wave. See, it's another thing we have to explain. We have to explain why, when the sun sends out light, it actually delivers energy through empty space to us. That's what we observe, right? So somehow, that electromagnetic wave, that light that's coming from the sun, is arriving here and bringing us energy, warming us, driving photovoltaics. So it's carrying energy. So we have to do that. Now, the way we do it in our course here is to say, suppose I have, well, first of all, recall that we did something similar to this. I think we did, or did we calculate the energy in a capacitor? The energy in a capacitor was a half CV squared. Did we do that in class? It's in the book. In other words, if you have a charged capacitor with a certain voltage across it, there's energy stored in the electric field. I don't know if we did that anyhow. And we did charge up a big capacitor and discharge the energy, got sparks. So that was kind of a proof that we have energy in the capacitor. Similar thing is going to go on here. Instead of the capacitor, oh, by the way, the capacitor is our model case of a uniform electric field. Bless you. The analogy in magnetism, the way to get a uniform electric field is to have a tightly wound solenoid. In that case, it turns out that the magnetic field inside the solenoid is uniform. That is, it doesn't vary from across the diameter. So the solenoid is our poster child for uniform fields. Solenoid. And what's nice about it is it looks like a pretty complicated thing to understand, because you have currents going around, coming out of something, going around, going into here, going around, coming back out of here, going around, coming out of, and if I try to do Biot-Savart law on all those currents, it looks pretty hairy. But the beautiful part is that this is very susceptible to the Ampere law solution. Remember, Ampere's law can do things by just taking, the Ampere law is that if you follow the B-lines around the loop, they will tell you the amount of current inside the loop multiplied by this convergence factor, U0. So very easily, if you have this solenoid with all these wires coming around it, you just draw your Amperian loop in a smart way, which is your choice, draw it right through the inside of the loop. You draw it this way, very, very far away, around to here, down to here, back to here. And then you just multiply b times the path length as you go around this loop. Now, by symmetry, because let's say the currents are going this way through the top, that means the magnetic lines are coming this way inside the solenoid. So b is this way, the way I drew the current. I put this Amperian line anywhere I like inside, and I just multiply b times the dr along this loop. And the point is, by choosing it this way, this part of the loop is perpendicular to the lines. So b dot dr on this wire here is 0. On this one, because they're perpendicular, b dot dr means the cosine between, and b is that way, dr is that way on this wire, and that is 0, so that gives you nothing. This one I put so far away that b is 0. I mean, whatever field there may be leaking, I know if I go to infinity, I can get b equals 0. In this one, the same story is that when I bring this line into the solenoid, the lines are this way, but the wire is this way, and they're at right angles, so that b dot dr is 0 here because the cosine of the angle is 0 between this line and this. So what you're left with is b times the length of that you're inside, and that is equal to mu times the current. And the amount of current going through here is the number per unit length. Let's see, it's the number per unit length times the length. So if you know how tightly wound this is, or how many wires you have per unit length, times the length will be the number of times current is trapped by this Amperian loop. And you cancel out, well, this is the same L. Make it a big L if you like. Cancel that, and you get that the B is equal to mu 0 by the number of turns per unit length. So that's very wonderful. That's you get an answer to a seemingly difficult problem. And so let's move on to a few more relatively mundane things. One of them, well, this is not so mundane actually. The idea is that if you have a changing flux inside a solenoid, and even if you go far enough away from the solenoid where the magnetic field is 0, you still get an induced electric field because you still have a changing flux through the loop. This I find a pretty amazing thing. In other words, I have a magnetic field here. I have no magnetic field here, and yet I can get a charge to move under the influence. The field isn't even there. The feeling would be, in order for a charge to feel something, it has to be right in that field. But here's some way I confine the field to this space, and I can still get an action on a charge that doesn't actually feel the field. That's remarkable, but it's true. In any case, there's some funny things about magnetic fields. That's one of them. We also define here the idea that if you have a particular device, like a particular spool of wire, a current through it will produce a certain amount of flux inside it. And the more current you put in, the more flux you get, the more magnetic field you create for a certain shape here. So it's reasonable to say that the flux that you get inside is proportional to the current. We call that proportionality constant the self-inductance, L. Again, that's very mysterious idea because we know what we're doing here. And then we can use the Faraday law that the electric motive force is equal to minus the change in the magnetic flux with respect to time. But, yeah, this minus sign, of course, due to lengths. But when we put in this little idea, we get minus the change in the flux, but the flux is L times I dt. And so that we get the electromotive force that you generate across this little spool of wire. L is a constant. It's part of the material. So you get minus L the I dt. What do I use? Big I's? Big I's. So this is the equation which is comparable to the other things we have had. Well, namely, the voltage across an element. We had that the voltage for a resistor is I times R. R depends on the particular object. We had that the voltage across a capacitor is Q over C. It's the charge on it inversely as the capacitor, and this is a property of the material. And now we're going to get that V, or EMF, is going to be equal to minus L the I dt. So these are the voltages across the three circuit elements that are used in electricity. What's interesting is that you have the charge, you have the current, which is the rate of change of charge, dq dt, comes into the resistor, and then the third one is the rate of change of the current with respect to the charge, time. So this is minus L, if you like, the second derivative of charge. So what you get is circuit elements respond to charge, moving charge, rate of change of movement. If you want to think in patterns, this is, I have to go into this more, but the point being that you want to realize that the structure, the L, the C, and the R are properties of the little resistor, of a capacitor. It depends on the dimensions and the material of the little object. The dimension of it doesn't depend on the voltage of the current. That you vary. But the only way to vary the L, C, and R are to vary its dimensions or the material from which it's made. We'll get into that next time. I think we're going to start next time, finish up on this a little bit, and then begin electromagnetic radiation, Maxwell, where these ideas reach another peak. So look, have a good weekend. Study well.